So everyone is there in the class, so we can start the presentation on the left. So the fourth experiment, we are actually going to measure the return loss, radiation pattern and gain of microstrip antenna. We have already done this for horn antenna in the second experiment, but microstrip antenna is a very popular antenna nowadays. So we'll try to measure the antenna parameters for microstrip antenna. These are the equipments required. You already know all these equipments. So the device under test is microstrip patch antenna. And we'll also use horn antenna, which is a little bit different from the usual horn antenna you have. Then we'll also have rotating mount, where you'll mount the antenna, DUT, and you can move it in clockwise and anti-clockwise direction. You can use BNA, spectrum analyzer, signal generator, and power supply. By now you already know what this BNA looks like. BNA ZBA24, it works up to 24 gears. It has two ports, port 1 and 2. Then this is a spectrum analyzer. It will be used as a it will be used for measuring the scattering parameters. Then you also have a signal generator. From there you can send the source. Antenna is a passive device, it needs a source. You can send the source at different frequency by setting up here. So this is how the microstrip patch antenna looks like. So this point here, you connect it to the coaxial cable. So now coaxial cable has inner conductor and outer conductor. Inner conductor should be connected to this microstrip line. This is called microstrip fit line. Outer conductor is connected to the ground plane. Ground plane is below. Ground plane is metallic surface on the other side of this board. You connect the outer conductor of the coaxial cable to the ground plane and inner conductor to this point here where you connect the microstrip fit line. So now it will come here, signal will come here. You have a notch here. You have a notch here. There is a small slot here. This is called a notch. This is a notch fit microstrip patch antenna. Usually at the edges of the microstrip antenna, it has very high impedance. So now this coaxial cable is of 50 ohm impedance, characteristic impedance. Microstrip line is also designed for 50 ohm impedance, but the edges of the microstrip antenna usually have around 100 ohm. So if you fit it directly at the edges, there will be a lot of reflection. So if you go towards the center, at the center impedance is 0. Towards the center, you have a 50 ohm location. You have to design that. So at that 50 ohm location, you give the fit line. So proper impedance matching. This is called a patch antenna. This is a double wrist horn antenna. This is actually just like your horn is an extension of rectangular waveguide. Double wrist horn antenna is basically extension of wrist waveguide. So your waveguide we have considered in the class, X-band waveguide usually have 8 to 12 gears of operation, but wrist waveguide can have very low operating frequency. It can start from 1 gears also. So this is actually wrist waveguide has been extended into double wrist horn antenna, just like you have extended rectangular waveguide to horn antenna, and it works at very low frequency. It can work from say 1 to 18 gigahertz. It has a very broadband operation. By now you already know what is a microstrip patch antenna. So this is a microstrip fit line, this is a patch, and this is substrate on which you are printing this patch. Patch dimension is given by length and width. Height of the substrate is h, and the electric constants of the substrate is given by epsilon r. You also have a metal printing here, which is a ground plane. Here we'll measure the return loss. Return loss is defined as 10 log of power input by power reference. So now if you have a relation between return loss and S11 parameter. S11 parameter was defined as 20 log of reflected wave divided by incident wave. So now if you convert it in terms of power here, so we have changed that reflected is here, incident is here. So you will have a negative signs. If you want to find return loss from the scattering parameter S11, then return loss would be minus 20 log of modulus of S11. So this is power input divided by power reflected. But when we define S11, it was ratio of the reflected wave by the incident wave. And this is power and voltage, you have a relation of square. That's why when you define in terms of S11, it would be minus 20 log of modulus of S11. And we are going to measure S11 parameters because antenna is a one-port device. Usually nowadays you have multi-port device antennas like MIMO antennas. It can have as many number of ports you want for higher efficiency, higher transmission. Usually, but antenna is a passive device traditionally. So, and it has one port, so you can just measure S11 parameters. You know what is the radiation pattern? Is the 3D pattern plot of the electric field in the far field of the antenna. So here you need to calculate the far field of the antenna is 2d square by lambda. You have to move a distance of 2d square by lambda, and usually microstrip antenna has dimension in millimeters, so the far field distance will be very near. So nowadays we have a lot of facilities. We have the anechoic chamber, everything. But when I joined here somewhere in 2005, some of usually connect the transmitting antenna here and a receiving antenna here, and see this vector network analyzer has one port, another port. You use one port as a transmitting, you connect the transmitting antenna here, in another port you can connect the receiving antenna. For the microstrip antenna measurement, this distance was even sufficient to have it in far field. You'll have little bit of coaxial cable also here. So with these two port also you can make antenna radiation pattern measurement for the microstrip antenna, because microstrip antenna is very small. So calculation of 2d square by lambda is not very large like that of the horn antenna. So even with these two port, we used to measure the radiation pattern of the antenna somewhere around 15 years back. But now we have anechoic chamber, we have all the facilities. We can measure it in anechoic chamber. Then in order to measure the gain of the antenna, you use the Friis transmission formula. You assume a transmitter is there, you have a receiver here. So they are placed at a distance of R, and receiver antenna and transmitter antenna has a gain of GR and GT, and power is transmitted from the transmitter is PT, and the wavelength of operation of the wave you are using is lambda. Then you can find out the power received. Power received is power transmitted, gain of the transmitting antenna, gain of the receiving antenna. Lambda is the wavelength of the signal you are using divided by 4 pi R whole square. R is the distance between the transmitter and receiver in the far field. So here, one thing you need to know is what is copolarization and cross polarization. So that should be very clear. Your copolarization measurement and cross polar measurement should be little bit different. It can be seen from. So these steps are already given in your manual, so I'll not read it out for you. Here we'll do one thing you need to understand is that whatever plot you are generating in the BNA, you want to measure S11 parameter, then you connect your antenna in the port 1 of the device, and you place S11 parameter in the BNA, then the plot would be generated in the BNA. After that, how do you post-process it? That would be also clearly shown by the tutors. So what you do is you can save your scattering parameter plot in the CSV format. You can save it and transfer it to your system, and you can plot it. So usually none of the books, none of the paper will directly show what is the output which is shown on the BNA. They actually transfer this file as a parameter plots in a CSV file, and you plot it in MATLAB. And that's the usual procedure. Otherwise, it looks very cumbersome. So there are two measurements here. One is the copolar measurement, another is the cross-polar measurements. And see, basically, antenna is a passive device. You have to connect it to the signal generator. So you connect the signal generator to the horn antenna, double wrist horn antenna. Then it will supply some signal here. Then it will transmit signal to the DUT. That signal received by the DUT would be measured using the spectrum analyzer. So what do you have? You have a signal generator which will give signal to the transmitting antenna, and you have device under test microstrip antenna which will keep in the far field, and line of sight propagation. There should not be any obstruction in between these two antennas, DUT and the transmitting antenna. Then you measure the receive power using the spectrum analyzer. So now this measurement is not only one time. You have to rotate it in both plane, in clockwise and anti-clockwise direction, like you have done for horn antenna. You can also find out what is the 3 dB point also. So now this measurement you have done for the copolar case, this antenna and this antenna should be in the same polarization. If you want to measure it for cross-polar case, you have to rotate this antenna in the 90-degree plane in the orthogonal direction, and you can still measure with the same antenna here. Then you can get the cross-polar measurement. So all these things should be clearly discussed and shown by the tutors. I have seen the video recording is clearly explained there. And one more thing, you can also measure gain of the antenna. Gain of the antenna is, you can usually measure if you are using, for example, you know what is the GTC. We have used double wrist horn antenna as a transmitting antenna, and DUT is the microstrip patch antenna for which I want to measure the gain. So now you have the same setup like you have done for radiation pattern measurement, but you know what is the gain of the transmitting antenna. And gain of the transmitting antenna in this case is 8.19 dBi. There should be I here. So dBi means dB isotropic. So you know the gain of the transmitting antenna. You want to measure gain of the receiving antenna, DUT, which is a microstrip patch antenna. You know the signal frequency, what signal you are used for sending the signal through the antenna. You know what is the frequency, then you can find out the wavelength. You know the distance between the transmitting antenna and receiving antenna, that is R. It's in the far field. Then you can measure the receive power. Once you have the receive power, you know what is the transmitting power, you know what is GT, you know what is lambda, you know what is R, you can find out the gain of the receiving antenna. So you can measure the gain of the receiving antenna by using Friis transmission formula by utilizing transmitting antenna and with a noun gain. Gain is already given to you. So this experiment is actually very similar to your second experiment, and equipments you are going to use, you already know all these equipments. So I'll not discuss much time on the discussion. We can wind up here. You can see the video clearly. Thank you.